Hi, so I would like to digest what we have found, what we have done, make it more physical. So it's not just math. So digesting the particle in a box solution. So first, let me recap what we're doing. We want to focus on well-like potential energies, confining potential energies that have two classical turning points. Classically, it would describe a particle that undergoes some sort of oscillation. We decided to look at model potential energies that are easier to solve. And one possible model of a confining potential is one that has potential energy, say, 0 outside a certain region and a negative U naught, or some negative value within that region. And then you would have two classical turning points. So that corresponds classically to a particle bouncing back and forth with constant velocity. So it's also kind of an oscillator, not a simple harmonic, but it's easier to solve. And then we simplified even further to an infinite well. What does infinite well correspond to? It corresponds to a potential energy, i.e., therefore, and therefore force, that confines a particle within a certain region, box, no matter how large that particle's kinetic energy is. Particle cannot escape. So particle in the box or infinite well physically corresponds to a situation of confining forces that prevent particle from escaping from a certain region, but within that region, no forces. So classically, it's like a bead bouncing back and forth, ping, 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 ping. That's what classically it is. It sounds like a strange thing to look at. Why would we want to study this model? The short answer is that it's easy to solve. So these are our training wheels. But even this very simple artificial model contains enormous amount of richness, and the features of the solution that we're about to discuss, many of them will persist to more realistic models. That's why we're doing this. So infinite well or particle in a box describes a particle that is confined within a region. We're doing this in one dimension, so that's within a number line, but really within a region of space. Now we like to put roadmaps and everything, so we have a region that's 0 and L. No matter what, it cannot be outside, and its particle is free inside this region. Classically, such a particle would just go ping, 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 with a constant velocity in between. What happens quantum mechanically? And we found what we do quantum mechanically is solve Schrodinger's equation. And then we need to unpack the results. So we found that energies form a ladder of levels, level 1, level 2, level 3, level 4. and these levels are discrete. So such a particle quantum mechanically can take on only very specific energy values, but nothing in between. That's already very different from classical physics. In classical physics, this ping, ping, ping particle can do the motion with arbitrary energy. Whatever initial kick you give it, it will keep that energy. So classically, the energy spectrum is continuous. It can have any energy, albeit the energy is kinetic, but it can have any value of energy. Quantum mechanically, it can only have discrete set of energies. So that's the first interesting feature. And the energies are given by h bar squared pi squared over 2ml squared times n squared. So n equals 1, 2, 3, and so on. And so this bunch of constants, right, this glob of constants, it's really the energy of the first level. It's called ground. So E1 is called ground state energy. This is a fancy lingo for a lowest energy level. So energies are discrete. Discrete. In contrast to a classical particle in a box, which would have continuous set of energies. We also found the wave functions, the full wave function. It's a function of x and t, and it's given by 2 over L sine k sub n x e to the minus I e sub n over h bar t, where k sub n are given by n pi over L, and E sub n I just stated, and that's the wave function. So these are full wave functions of a particle in a box with specific energies. So a particle in a box can occupy one of these levels, and if the energy of the particle is given by one of these, the wave functions will be given by one of these. We discussed that it's possible to have a particle in a superposition of states. If it's in a superposition of states, it doesn't have a well-defined energy. If you measure the energy, you're going to find one or the other, depending on what kind of superposition it's in. We will see more examples of superposition states, but right now, if a particle is described by either psi1 or psi2 or psi3, its energy is correspondingly E1 or E2 or E3. General wave function can be a superposition of these, but then it doesn't correspond to a pure energy state. It doesn't correspond to a well-defined energy. Meaning if you were to measure the energy of a particle in a superposition, for example, of psi1 and psi2, then you might get energy 1 or energy 2 with certain probabilities. We will do more of that later when we discuss superpositions. We've already had some exposure to superpositions, right, up until this point, and we will come back to it. So that's the summary. And now what I would like to do is I would like to digest this. So if you look at the, let's do energies first. So digest energies first. If you look at this formula, E sub n equals, let me just copy it down, h bar squared pi squared 2ml squared times n squared, which is really E1 times n squared. You look at it, and it looks like a bunch of math. It doesn't have any meaning to you. It's just a bunch of constants. It looks pretty scary first time you look at it. We can try to get some intuition for this. I can try to explain where this comes from by an intuitive argument. So this formula was derived rigorously by solving the Schrodinger's equation. But here comes the intuitive argument. So that you can gain some relationship with this. Notice that inside the box, the particle is free. The particle is not totally free. It cannot move with a constant velocity from x equals minus infinity to x equals plus infinity. It's confined. But at least inside the box, the particle is free. And we've already seen that a free particle has a certain relationship between energy and momentum. So inside the box, the particle is free, no force. For a fully free particle, even in quantum mechanics, we already saw that there's a relationship between energy and momentum. And it's the same as a classical relationship. You can write 1/2 mv squared. You can rewrite like that if you take P equals mv. And in quantum mechanics, the same relationship between energy and momentum holds. Also, in quantum mechanics, there's a de Broglie relationship, h bar k. And so you could say that energy equals h bar squared k squared over 2m. This much is true for a free particle. So if a free particle is described by a wave function with a particular wave number, the energy, kinetic energy of that freely moving particle would be given by this formula in terms of that wave number. So that much is true. However, for a free particle that's not truly free, but that's confined to a box, we saw that k can only take on discrete values of discrete values, where n equals plus and minus 1, plus and minus 2, and so on. For a truly free particle, k can be anything. You can have wave function with arbitrary wave number. For a particle that's free but confined to a box, not truly free, k's have to take on discrete values. That comes from boundary conditions. Then if you plug that into here, and get you get the formula we derived, h bar squared pi squared 2ml squared times n squared. So the argument is a little bit nuanced. It's like poetry, that the more you analyze it, the less exact it becomes. So it's not a rigorous argument. It's an intuitive argument. So you could see, oh, I see, at least I can relate to this bunch of gunk in this formula. It looks like a bunch of math. But you can intuit this result from this kind of an argument. So that's point number one. I would like to make another point about energies. So it's not just a bunch of math. I can rewrite this like this. I can rewrite it like this: h bar squared pi squared over 2m times n squared over L squared. And so what I see is that energy is proportional to 1 over L squared. So what this means is that if you have a narrow box versus a wide box, the energy levels are lying closer together. So if you have a narrow box, here's the first energy level, here's the second energy level, here's the third energy level. If you have a wide box, here's the first energy level, here's the second energy level, here's the third energy level, and so on. So you see that E1, E2, E3, E1, E2, E3. So if you confine a particle to a smaller and smaller amount of space, it will have larger and larger energies. Does that make sense? This is an interesting result. You may not have thought of it when you looked at the formula. Well, it does make sense, right? Because if you want to confine a particle to a smaller and smaller amount of space, you have to do more and more work on it. And then the energy gets stored. The energy of the particle it comes from the energy that you put into it by doing work to confine it. That's, again, an intuitive argument, right? So you have to put more and more energy into it. So if you were able to confine it within the smaller and smaller amount of space, it will have more and more energy. This also makes sense in terms of what we know. Let's think about atoms versus nuclei. Atoms are much larger than nuclei. Now, an electron inside an atom is described not by a particle in the box, but it is a well. It's some kind of a well, and we will maybe see if we have time that electron in an atom also has a ladder of discrete states. What is the typical energy spacing for electron in an atom? It also has discrete energies. And if I had to ask you, what are the values of those discrete energies? Maybe you will have an intuition at this point, maybe from your chemistry class, that a typical energy associated with chemical reactions is on the order of magnitude of electron volts. For example, electron in a hydrogen atom can occupy the ground state, first excited state, second excited state, and so on. And the energy that you need to supply to an electron to completely ionize the hydrogen atom, to rip out that electron, is 13.6 electron volts. It's a very well-known number. If you want to move electron from the ground state to first excited state, it's going to be less. I forgot what it is, like maybe 4 or 5 electron volts. And if you have chemical reactions, well, chemical reactions overall lower the energy of the combined system. So if you have a hydrogen atom and a hydrogen atom, each electron occupies a certain energy. And when a bond forms, each electron has a lower energy. The difference in the energy there is not going to be 13.6 electron volts, but it's still going to be on the order of a few electron volts. So chemical energies and or energies of electrons in an atom are on the order of magnitude of electron volts. Nuclear energies, which again includes the spacing between nuclear energy levels, say proton within the nucleus, and or the energies that can be obtained from nuclear reactions, are on the order of magnitude of millions of electron volts. So it's a factor of million times larger. And energy spacing of, the nuclear energies, the energy of protons and neutrons within nuclei, they are something like 1,000,000 times larger than the energy spacing of electron energies within atom. You can roughly see where that factor of 1,000,000 comes from, is that nuclei are something like 1,000 times smaller than atoms. So the idea that nuclear energies are something like 1,000 times larger than electron energies is consistent with this formula. This is not nuclear physics right here, but even such a basic model like a particle in the box already tells us the scaling of energy with the system size. The energy goes like 1 over the system size squared. So if you squeeze something by a factor of 1,000, the energies are going to spread by a factor of 1,000,000. So you see, this simple model already knows about this. So that's point number 2. And I will either discuss it in an example at the next lecture, or maybe I will make this into a homework problem where you can digest this a little bit more. Point number 3. Oh yeah, and correspondingly, there's also 1 over the m scaling of energy with the mass. So I'm not going to go there, but it's not just a mass sitting. It tells us that energy scales like 1 over the mass or 1 over the length squared. That's interesting. Point number 3. Well, we see that energy is proportional to n squared. So it's a ladder of energies where the energy spacing gets larger and larger and larger. That's what this says. But let's actually calculate the energy spacing between n and n plus first level. So E sub n plus 1 minus E sub n equals E1, n plus 1 quantity squared minus n squared equals E1, n squared plus 2n plus 1 minus n squared. So the exact formula is that it's 2n plus 1 E1. You could plot this, and for large n, this is delta E. You can plot delta E versus n. You see it starts with a non-zero, but for large n, this offset is not important. So you can see that delta E scales like n. So energy scales like n squared, but the energy spacing is proportional to n. You can also take a derivative. When you take a derivative of n squared, you get something like n. So the fractional difference between successive energy levels scales like n over n squared. I'm just looking at the scaling. And so this is equal to 1 over n. So while the energies actually get further and further apart, relative to the energy itself, they don't get further and further apart fast enough. And so that if I look at an extremely excited state, like n equals 1,000, way out there, right? If I extend this ladder to 1,000, and I kind of zoom out, the energy spectrum looks essentially continuum. That's what this is telling me, that energy spectrum of very excited states. So the state wave function with the lowest energy is called the ground state. The next one is called first excited state. and successively it's called second excited, third excited, and a very high end is called highly excited state. That's the word excited. That's where the word excited comes from. Very excited states look almost continuous. Nu or And what does that mean? What's the physical significance of that? It says that while for low-lying energy levels, low-lying states, energy is discrete, in contrast to classical, where it's continuous, the highly excited states behave kind of pseudo-classically. That's what this really means. Highly excited states are sort of more more classical or classical-like. For a particle in a pinball machine, it can have any energy, 13 joules, no problem. 13.012 joules, no problem. 13.012345 joules, you got it. Quantum mechanics, not so much. You can have either E1 or E2, but nothing in between. But for very excited particles, it's almost a continuum spectrum. Not really. There's still spacing between, there's still energies that are not allowed, but relative to the energy itself, the spectrum looks more and more continuum. And we've already seen this. We've already seen that the quantumness of particle, well, it pops out in certain situations. It depends on the context. We've already seen that. But generally, large things like ourselves, we behave classically. Well, we contain a lot of, we're very energetic objects. When I walk down the street, my energy is not measured in electron volts, it's measured in joules, which is many orders of magnitude more than electron volts. So this somehow matches the intuition that things that are very energetic should behave classically. Again, it's also an intuitive argument. These are all intuitive arguments that are designed to make you feel more comfortable with the material so that it doesn't look like just a bunch of math. You see, there's a lot of physics contained here. So I made 3 points about energies. Now let's talk about the wave functions. So part 2, digest wave functions. Well, first of all, let me write them again. I'm not going to put explicit dependence. Let's see, can you make sure? Yeah, I'm not going to put the explicit dependence on space and time. You should get used to that. It's given by these things. And let me write it like this. So omega sub n equals E sub n over h bar. So that's the de Broglie relationship. When we looked at the string, just a classical string, regular string, like in introductory lab, we saw that a string can have arbitrary energy, but not arbitrary wavelength and frequency, because those have to obey the boundary conditions. But quantum mechanics relates the frequency of the wave function. So omega is the frequency of the wave function, relates the frequency of the wave function to the energy. So the discreteness of frequencies, which is there even in classical physics, tells us that there is going to be discreteness of energies. Classical physics does not relate energy to frequency. I mean, the energy of the string does depend on the frequency, but there is not a de Broglie relationship So while in classical strings, frequencies are discrete, but energy also depends on other things, for example, on the amplitude. And therefore, the string can vibrate with any energy that you want. You can have a first mode, and you can have a string in the first mode to have arbitrary energy depending on its amplitude. You can have a second mode, which has a different frequency, but you can have the string vibrating in the second mode to have arbitrary energy because that depends on the amplitude. Quantum mechanics says that a particle that's described by a wave function has an energy that's related to the frequency of the wave function. And because the boundary conditions dictate that wave numbers and therefore frequencies have to be discrete, it implies that energy also has to be discrete. So the relationship between energy and frequencies built into the solution. How do we calculate the probability? The probability of finding the particle in a particular wave function, or in a particular wave function state. Well, let's just psi star psi, and hopefully by now you feel more comfortable with this, and you can see that when you take the complex conjugate, it conjugates the complex exponential, and so this becomes like this. So let me plot a few of these. So here's the probability density. Remember, this is a probability density. It's not the probability, it's a probability density. So here is L. What is K sub n equals pi over L times n. So for n equals 1, you have pi over L. So when x equals L, you have sine squared of pi. So it goes back to 0. So it looks like this, right? It's largest in the center. Looks kind of like a bell-shaped curve. It's not a Gaussian. It's just a sine squared. That's what a sine squared looks like over one period. So this is first mode or first level. So n equals 1. And notice that probability densities do not depend on time for a particle that's described by one of these modes. It does depend on time when a particle is in a superposition state. But when a particle is purely in one of these modes, either in mode 1 or in mode 2 or in mode 3, the probability density does not have time dependence. A wave function has this oscillatory time dependence, but probability density does not. And for this reason, modal wave functions are also called stationary states. Your textbook calls them stationary states. What's stationary about them? The probability density is stationary. Stationary means does not change in time. So I can plot the probability density. So this is P1. I can plot the probability density of the second mode. So this is X. Here's L. So now it's sine squared of 2 pi x over L. There will be a node in between. So it looks something like this. So for the first mode or first stationary states, there were no nodes in the center. For the first excited state, there's one node in the center. There are also two nodes on the edges because of boundary conditions. I'm not counting them. So this is second mode, n equals 2, and it has one node in the center. And the third level, the third state, the third excited state will have the following probability density. So now, well, there will be two nodes. right? And also on the edges. And the probability density would look kind of like this. Right? And so on. So this is n equals 3, and you have 2 nodes. And so this is very interesting. So this says if a particle has energy E1, then if you were to try to measure the position of that particle, you will get, first of all, the most likely position will be right in the middle of the box. And if you have an ensemble of particles, each having energy E1, and you just measure away position of each one. You measure position of the first, you measure position of the second, you measure position of the third. Each time you measure, you record. So you don't remeasure position of the same particle. You lay out all these particles, a trillion particles, each prepared in the state psi1, each has energy 1, and then you measure position of one, you record that number. You measure position of the other, you record it, and so on. And you build a histogram. When you normalize that histogram, you're going to get this thing, P1. So you're most likely to find particles here, maybe a few outliers here. That's what this means. And it's very non-classical. In classical mechanics, first of all, there's no fundamental notion of probability. Yes, you can have probabilities if you choose to have ignorance about something. But if you know the initial condition of the particle, you know its fate, you know its trajectory. So in classical mechanics, probability is not really a fundamental thing. The way that you would describe a classical particle is just position as a function of time, right? So you could you could plot it like that, and that's what it is. In quantum mechanics, we don't do trajectories. We have statistical predictions, and that's the statistical prediction. So that's compare and contrast classical versus quantum, a particle in a box. If the particle is in the second excited state, so in the first excited state, it has energy, in the first state, it has energy 1, in the second, it has energy 2. So if you have an ensemble of particles in the box, in this kind of a potential energy well, each of them has energy 2, then when you perform an ensemble of position measurements, you're going to get a bunch of positions clustered around these two spots, right? So these are the most likely values, either this one or this one. You're also quite likely to get positions in the neighborhood of these most likely values. Again, that's not a classical behavior. So that's what it means, right? So I'm trying to build comfort around statistical view of particles. There is more. I can say a little bit more. Now, I said in classical mechanics, probability is not fundamental, but I can think of probability in the following sense. Imagine I have an ensemble of classical particles, ping, 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 and each of them has a random initial condition. So that's my ignorance. I choose not to know their initial condition. So imagine a room full of these pinballs, and they're making awful noise. And you will just kind of hear white noise because some are going to the left, some are going to the right. And if you randomly pick a particle at any one time, you're equally likely to find a particle within any bin of your coordinate. So in that sense, you can talk about classical probability density. It's not really a probability density, but you can bring in the notion of probability in the classical sense. And so the probability density would have the following value. It's P naught. What is P naught? Well, remember, probability has to be normalized. So P naught times dx between 0 and L has to be 1. Okay, so P naught L equals 1. So P naught equals 1 over L. So P naught equals 1 over L. If you perform a position measurement, what's the probability? Remember, this is a probability density. Probability of finding a particle within a region of space of with delta x. So this is probability to find the particle within delta x, some x naught. So let's say this is x naught, and I have a bin around x naught. And delta x could be set by the resolution of the measuring apparatus, for example. So the probability is given by the probability density times delta x. So that's P naught times delta x, which is delta x over L. So the probability, the chance, the likelihood of finding a particle in this kind of an ensemble over randomized initial conditions, the probability to find a classical particle in this type of scenario would be given by this formula, to find it within delta x. Now let's go back to quantum mechanics and let's look at highly excited state. Look at a highly excited wave function, highly excited state. N equals 1,000,000,000, something like that. What's the probability density look like for that thing? It will be highly oscillatory, right? Highly oscillatory. I'm going to get tired of drawing this. This is less than 1,000,000,000,000, highly oscillatory. Again, I can ask, what's the probability to find a particle within delta x? And let's say delta x is much larger than the wavelength of those oscillations. Question, what's the probability to find the particle within delta x that is much larger than the wavelength? So it includes many cycles. And again, delta x could be set by the resolution of the measurement instrument. Let's say your measurement instrument it doesn't have an infinite resolution. It can only say plus or minus a millimeter. So the best that the measurement instrument can identify where the particle is within a millimeter. It just cannot do any better. So it makes sense to ask such a question. Well, if I zoom in here, what I see is these oscillations. This is the sine squared oscillation. And because delta x is much larger than the wavelength, it would have many cycles. And you see these cycles go between 1 and 0. So this is 0, this is 1. So the probability to find this is my delta x. It's a big delta x in comparison to the wavelength. Find a particle within this region is, well, that's what you have to do, right? You have to be a good sport. You have to, that's the probability. This big P is a probability density. Well, that's really the area under this curve. And you can see that it's half of, sorry, this is 1 over L, right? You see the probability density, it oscillates between 2 over L and 0, 2 over L and 0. So this is 2 over L. I'm glad I caught myself. This is 2 over L. It goes between 0 and 2 over L. And so you don't have to do any math. You can see that it's half of that area. It's 1/2 of that area, 2 over L and delta x over L. So you can see again that in highly excited states, there's a correspondence with classical physics. In ground state, that's not true. The probability to find a particle within this bin right here is not the same as the probability to find a particle within this bin. It's clearly different, and it's not equal to, it's not a constant, and it's not equal to delta x over L. But for highly excited states, basically the probability density averages to 1/2 of these oscillations. So it goes between 0 and 2 over L, 0 and 2 over L. So it averages to 1 over L. And we sort of get back the classical behavior again. We see that again. So reminiscent. No, we choose the words carefully. More classical. So you see that these results that I started with, the set of energies and the set of wave functions, there's a tremendous amount of insight in them. There's a tremendous amount of physics in them. So these are excellent training wheels. Particle in the box is an excellent training wheel. And moreover, we see that certain features, we will see that as we look at other examples of quantum bound states, certain features are found in all of them. You have progressively higher number of nodes and antinodes as you go from to higher and higher excited state. The curvature of the wave function progressively increases. The energies are discrete. The energies progressively increase and so on. There are a lot of commonalities here. And after seeing a few examples, I can give you a quantum problem that you don't know how to solve, and you will be able to intuit about the behavior, wave functions, and energies in that quantum problem without even knowing how to solve it exactly. So that's why we're doing this. And a particle in the box is an excellent training wheel, so treat it with respect. It's not some artificial thing. Okay. What's the next thing to do? Well, we have probability densities. We can ask statistical information. We can calculate averages, average position. We can calculate standard deviations. We'll do that in the next video. This is too much for now. Okay. All right. Well, thank you.